it's dx by dt, and then as a sort of intermediate step, it's taking this original definition and just making the time interval really small. That's what calculus does for it. Good. So now we've got the definition of average velocity over some time interval, and we've got a definition of instantaneous velocity at a particular time. So not a time interval, but at a particular time. Good. So let's take this one further step, and then we're almost done in defining our variables. Velocity has specifically, of course, to do with cases where we're looking at the change in position as a function of time. But maybe we can go one step further and ask the question, what about in cases where the velocity itself is changing as a function of time? The red curve would be a perfectly good example of this. And this leads us naturally to the definition of acceleration. And following what we have up here, I'm going to define the average acceleration as the change in now velocity over time interval rather than the change in position over time interval. v2 minus v1, t2 minus t1, and as we did before, more often than not, it's actually more useful or interesting to know what the acceleration is at a particular instant in time. So I'm going to do the same prescription that I had above for velocity, and of course, you know how this goes, although that looks exactly the same, but taking it to the next step. And again, you're all comfortable with integration, so you also know that I can write this as the second derivative of position with respect to time, d2x by dt squared. Okay? So now we've got all our kind of necessary variables defined. Let me just quickly check that I haven't missed anything important that I wanted to say. I don't believe I have. I'm going to pause and ask for questions on these definitions. Good? Okay, so now we've got our sort of language lined up. I want to say something about the sign of acceleration, and at some point maybe we'll do a worked example in class later on this morning. But let me just say something about the sign of acceleration and words that we often use. If the acceleration is in the opposite direction to an initial velocity, quite often we use the word deceleration in this case. Okay, just think about that. So the assumption here is that this thing, as we start observing it, start measuring it, it's already moving with some velocity. But then, if there's an acceleration, which is in the opposite direction to that initial velocity, again, think about this a little bit. What is it doing? It's tending to decrease the velocity if the sort of it's defined in a certain direction. So the acceleration is in the opposite direction to the initial velocity. We call it vi. We've got an acceleration here. This is tending to slow it down, slow it down, slow it down, slow it down. If this acceleration was maintained, what would happen eventually in terms of the direction of the velocity?
It would go the other
Switch. Good. Okay. So I just want you to be aware of that. I will try and avoid the word deceleration. I think it can be confusing. I'd much rather say it's an acceleration in the opposite direction to some initial velocity. Okay? So just be aware of that. Good. Okay. So we've got our list of variables. Now I said we need to worry about a little bit of calculus. And we do. Very often we will have motion that is described in terms of a function. Okay, so by function, I mean we might have, for example, that x is explicitly time dependent, so x is a function of t. Entirely possible. We just just pick up a simple example that I happened to pull out when I wrote my notes. I'm going to write this. As one example. Okay, so slightly maybe contrived, maybe a little bit unusual in nature to find motion of this particular type, but why not? Let's see if we can understand what's going on here. Well, first off, what I want you to think about when you look at this is the idea of dimensionality that we talked about last week. Namely, if I've got an equation, it better be true that every element in that equation has the same dimensions. By every element, I kind of mean everything that appears, I never know how to say this, it kind of appears as a separate term in the equation. It must have consistent dimensionality. What do I mean by that? This is a definition of position as a function of time. So this is definitely has dimensions of length, might be in meters, for example. If this equation is true, everything on the right-hand side, every term, when taken as a complete term, must also have dimensions of length, meters, let's say. Otherwise, it is not a true equation. It doesn't work. And these are the sorts of things, as you get further into physics, you'll want to be checking on as you go along. So the question is the way that we've been given this function, is it correct to begin with? Well, hopefully the answer is yes, and we'll just quickly check that it is. So I have three terms here, and it better be true that each of these three terms has the dimensionality of length. Clearly the first one does. It's defined as being simply a constant position, or offset, if you will. So this is certainly right. This one has time in it to the power 1. In some sense, you could think of this as time to the power 0. Now I have time to the power 1. That, of course, has dimensions of time. So in order for this term as a whole to be consistent with the dimensionality of distance, I'd better multiply it by something which has dimensionality of distance over time. Okay? So in fact, I have something which is distance over time. It happens to be a coefficient, meters per second. So dimensionally speaking, we're in good shape. Same thing is true over here. I've got t squared, so I better have a coefficient here that has units or dimensions of length over time squared. So this is all good. Now, I just want to give you a caution here, because you'll find in the Master in Physics and the Sears textbook that occasionally they forget units. And that's kind of bad, particularly as you're starting out in a course. So just be aware of that. Again, they're very lazy in the textbook, quite often in the early chapters about putting units in here. Remember, they must be there to have this dimensionally consistent. Okay. All right, so let's do a bit of quick differentiation. If this is x as a function of t, what does the instantaneous velocity as a function of t look like? Go ahead. -4, let me write it like this, -4 meters per second plus 4 meters, yes, plus 4 meters per second squared times t. That should be right. Everyone okay with this? What have I done? And this is the thing I didn't get right out, but I think all of you know it. All I've done is remind you of how to differentiate a simple polynomial function. And that's by and large the only thing we're going to be doing for a while. So for example, here I have, let's take some generic term, x equals some constant times t to the power n. And what I'm hoping you guys will remember is when I differentiate this now with respect to t, because x is a function of t, I need to bring the power, the original power of t, to the front as a multiplier. I keep the original coefficient. I still have t, but now I have to drop the power of t, so that's t to the n minus 1. Okay? So hopefully you're all very comfortable with this. I'm going to assume you are. Simple differentiation of polynomials. We're good? Yep. Okay, so the question was, when doing work, you need to show units. So this course is going to be a little, this is one aspect about mastering physics that I don't like, perhaps the only one. Because of course you're submitting answers in mastering physics and you're not showing work. contrast, when you do tests, you're showing work and you're of course showing answers. So I will ask that you show your work on tests. And I'm trying to figure out if I want to give you some exercise on that outside of mastering physics, just so that you're in the habit of showing work. So the question was, should I show units? I'm agnostic about whether you show units during a calculation. I'm not at all agnostic about whether you show units at the end of a calculation. You must show units at the end of the calculation. Otherwise, somebody will come along and wrap your knuckles, okay? So make sure when you give answers, they always have units. I will be a stickler about that. Science and physics makes no sense when we're talking about quantities that are measured or observed. They need units. So you must do that. As you go along, it's kind of up to you. I'm lazy. I usually don't because I'm lazy, but I do make sure at the end that I do. And I'm fine for you guys to do the same. If you're nervous at all about carrying units correctly, just keep them throughout. If you're confident, don't, because it's a waste of time, sort of. That's kind of my approach, all right? Instantaneous acceleration, second derivative. What's this? Okay, good. So now you've gotten used to doing a first example of being given an explicit function of position as a function of time, differentiating it to get instantaneous velocity, instantaneous acceleration. I was a little bit lazy here as well. I've already started dropping instantaneous here. You'll find our textbook does that as well. Usually we're interested in instantaneous quantities rather than average. And so since instantaneous is kind of the thing we focus on most, you can kind of get lazy and simply drop this and assume that you understand that he's talking about instantaneous. Good. Okay, I have the feeling you guys are all super up to speed on all of this. So I don't think I'm going to dwell on it too much more. But okay, I'm going to do this a little bit later on as we talk about constant acceleration motion. I am going to have you guys work through a quick worked example in about 10 or so minutes, because I want you always, as we start getting into working problems with this, to be asking yourself, when you've done a calculation, does my answer make sense? Okay? So, kind of an obvious thing, but not always done. So make sure, as you start doing calculations, that the answer that you get out does make sense. It means it's dimensionally consistent. It means it has a numerical value if it has one, and a fair number of our work problems will, though sometimes they'll be algebraic. If you get an answer that is, 10 something times 10 to the power of 35 or 10 to the minus 68, and we're talking about motions of macroscopic objects, those answers are probably not correct, okay? So does it make sense? Good. Okay, so now we've got the basics in hand. I want to turn our attention to the particular case of constant acceleration motion. So why is this of particular interest? I said by and large we're not going to address the question why things move the way they are, we're just going to describe how they move. However, it's worth looking forward a little bit right now, because this particular idea of constant acceleration motion turns out to be related to why things move the way they do. And as we'll see in a couple of weeks when we explore Newton's laws, maybe next week, one thing that turns out to be true in nature is that accelerations on objects can be related to forces that are somehow exerted on them. So this is a look forward, a couple of sessions at least, and I've written that in a way that's slightly different than you're probably used to. Okay? For those of you who've done some intro physics before, this is one of Newton's laws, and it relates the fact that accelerations of objects depend on net forces that act on them, and the concept of proportionality has something to do with the mass of the object. Okay? And of course, rearranging that equation gives us F equals ma, which most of you know. Not all of you, if you don't yet know that, that's just fine. But suffice to say that there are many situations in the world around us, and even the world not so much around us, but much further afield, where forces, of course, act on objects, and there are plenty of instances where those forces are constant. And if the forces are constant, what we learn from Newton is that the associated acceleration is constant. This is why constant acceleration problems are so prevalent, so important. Okay, so we're going to look at constant acceleration motion because there are lots of examples around us. And so quickly, I want to derive a little bit about some special equations that we can use for this case of constant acceleration motion. So the first thing I'm going to do is go back to this. Okay, now I'm going to do something annoying, which most textbooks do at this point, and since we've just got started, it's kind of particularly annoying, but I'm going to change variable notation. Okay. First time I've ever drawn a smiley in a class, but it's just kind of annoying. So why? The reason being that very often we, again, simplify our lives. In particular, we'll simplify our lives by starting observation or measurement of something at a time that we're going to call t0. So, let me just write up what we're going to do. I'm going to start off at some initial time, which we're going to choose as being our origin of time. So previously on these chalkboards where I talked about an initial time t1, I'm going to just simply call this t equals 0. And in fact, t equals 0, so it's going to disappear from some of these definitions. Later time t2, since t1 has now disappeared, get rid of this, is just going to become a generic t for some later time. The initial position, maybe, which was x1, becomes x0 because it's at the initial time. The later position, which was x2, just becomes a generic x, and so on and so forth. I'm not putting vector arrows on here just to save a little bit of time. Hopefully I've written all these changes out consistently. So just make sure you get the idea of what I'm doing. I'm going to set my initial time to be 0. So in some sense that's going to drop out of these previous definitions. Later time just becomes a generic t. And then positions, velocities, and accelerations if I carry on down the list. x0 for initial, x for some generic later time, v0 for initial, v for some generic later time. Okay? So, with that in mind, let me come back to the chalkboard on the left side and simply quickly rewrite that equation that I just wrote on the rightmost chalkboard with the new variables. Okay, so what did I have? The average acceleration, still the same notation. But now I need v minus v0 over t minus 0. Okay, good. But in the case of constant acceleration motion, what can you tell me about the relationship between the average acceleration and the instantaneous acceleration? Excellent. Okay. So this is now instantaneous, where I'm being lazy. So in fact, I can write that. This is the special case for constant acceleration motion. It's the only special case, obviously, where this is true. So now I'm going to take this thing above the dashed line and rearrange it. And what should come out is that V equals V0 plus A times T. You want to get in the habit of always checking my work, particularly when I'm doing manipulations. I often screw it up, but hopefully that's correct. All right, so now we've actually very simply derived what's called the first equation of motion under constant acceleration. I might as well introduce this right now. You'll probably see this a lot more in physics. Equation of motion, EOM, first equation of motion under constant acceleration. And what I'm also going to do as we get further into the course is throughout encourage you not just to sort of check for dimensional consistency, so on and so forth, but start what I describe as reading equations. What do I mean by that? This is a fairly simple one, so it's not terribly enlightening. But what I want you to do when you see equations for the first time is simply ask yourself, first off, what is it relating? And then how is the relationship expressed? And often a way to get some sort of physical intuition into these things is ask the question, what happens if some of these parameters take extreme values? By extreme, I usually mean that the parameter is 0, or it's infinite. It's about the extreme variety of values that parameters can have. And so look at each of these things and ask yourself, how do the other properties vary? How do they depend on each other if one parameter takes an extreme quantity, extreme value? Okay, just out of thin air. If the acceleration is 0, that's an extreme case for the acceleration, this term disappears. The velocity later on is always the same as the initial velocity. So think about it. Read the equation. Absorb what it's telling you about the physics. It's one of the best ways you'll start to build intuition, is to look at equations the first time they're introduced and ask yourself, what is it telling you? How does this depend on this? Okay, so there's the first one. Easy enough. Let's take a look and see where else we can go with this. We also know that the average velocity can be defined as now new variables, x minus x0 over t minus 0. In this case, the instantaneous velocity and the average velocity are not the same. That's not our special case. The only thing we've required is that the acceleration is the same. But in this case, in generally, or not even in general, the instantaneous and average velocities are not the same. But there's something else we know about the average velocity, because what we've just learned here is that v is a linear function of time. So if I was to plot now velocity as a function of time, well, okay, it depends what v0 and a are, but generically speaking, if I was to ask you to show me what v as a function of t looks like on this plot, what generically does it look like? It's a straight line, right? I don't know its slope, and I don't know its intersect unless you tell me a and v0, but it is a straight line. So then the question I'm going to ask you, and it's maybe not entirely obvious, I explicitly started this at t equals 0, so I better start it at t equals 0. Here's v is v0. So the question is, if I've got a linear function of velocity as a function of time as a linear function, what can you tell me is another way of writing the average value for this? You may or may not get this. But it's going to relate the average value to the initial and final velocities. Yeah?
It would be it would be final velocity minus initial velocity over time. Or
goodness, to see if I can get a couple more inputs on this, just to sort of see what people are thinking. Yeah?
Would it be like the square root of b squared plus b squared?
Don't make your life complicated. Yes.
Wouldn't your final velocity minus your initial velocity divided by 2? Like give you your average.
Almost. Just say the first bit again.
Your, oh yeah. But
Go ahead.
yes, you add, sorry, yeah, you add your final velocity with your initial velocity, and you divide it by 2 to get
Right.
your average.
So it's a linear function. So in fact, again, don't overthink it. It's a little bit out of context in this setting, so it's not obvious that you would get it. But as you would define the average of anything that is linearly dependent like this, in fact, it is simply the initial plus final velocities divided by 2. Okay? So we're going to make use of this. Take this and this as equivalent, and if I combine them together, what I should get, I'm going to simplify this right off the bat just to gain a couple of seconds of speed, is the following. X minus x0 equals, and again I'm doing a little bit of combining of terms here, right off the bat. But hopefully you guys can scroll this on the side of your notes and convince yourself it's true. I would find this is true. Okay? So all I've done in both of these cases is assume that the acceleration is constant. And in this case, it's a slightly more involved expression, but not by much. This is the second equation of motion under constant acceleration. Okay, so fairly straightforward. I will add for completeness that, of course, we have now equations that relate different combinations of our fundamental variables. What we can do is do some substitutions to get permutations of these original 2 equations, and in fact give us a larger slate of equations of motion under constant acceleration to play with, which is what we're going to spend the remaining 15 minutes of class doing. But let me just first write up what the other permutations of these pieces of information look like. So, preempting the question, where's what I'm about to write down come from? It's simply taking these 2 initial equations, taking some other definitions that at this point may or may not still be on the chalkboard, doing a substitution and cleaning up. And what you will find is that you can also get equations of the following nature. Again, it's just simple substitutions at this point. There's one. Here's another. Or even this one. So these are sometimes described as secondary equations of motion. Don't really know why, but they are. So we can get these permutations, okay? What we end up with is 2 plus equations that we're going to use only in the case of constant acceleration motion. This is going to dominate our work, obviously for the rest of today and maybe to some extent for the rest of the week and also in your upcoming PSET 1. I want you to make sure that you don't get carried away with doing constant acceleration problems. You always have in the back of your mind the question, is this a constant acceleration situation? Don't get so tied to this that you apply it unthinkingly. This all has to apply to constant acceleration motion. So what are we left with? We're left with a handful of equations now that will relate our kinematical quantities under constant acceleration. And we're often going to be presented with problems where we're given certain pieces of information and we're asked to calculate what's missing, so to speak, the variables that are unknown. So that's an absolutely standard sort of problem. So a few sort of words about problem-solving strategy, and then I'm going to have you guys problem solve. Okay, so is a constant very important? If no, throw up your hands and say, I don't yet know how to do this. A has to be constant for you to use these equations. So we will be, of course, given problems with known variables, quantities, and one or more unknowns. Of course, that's what we have to find. Just a footnote here. Again, you're using mastering physics for homework, so this doesn't really apply.